One application of derivatives is to determine the tangent and normal lines of plane curves. This is the first example. You are watching differential calculus. There is a pattern in solving for the equations of the tangent and normal lines of plane curves. The first step is to look for the slope of the function by taking its derivative. With a provided point, you surely will be able to find a numerical value for the slope. This parameter is used through different line forms, depending on what complementary data is given. The first format for the line is a slope-intercept form, which is y as equated to mx plus b. This is used when y-intercept is given along with the function. The second line format is the point-slope form, which is y less y1 as equal to the slope m times x less x1. This is used when the complementary data given are coordinates of a point. Both line formats result to the tangent line of the plane curve, so next is to solve for the normal line. With the same procedure, one only needs to change m tangent into the normal slope, which is basically just the negative reciprocal of the tangent slope. Plug these into the line format of your choice and have the normal line function. Take note that we are to look for the slope using derivatives and partner it with those line formats which have slope too. This is the main reason why slope-intercept and point-slope formats are usually incorporated. The problem includes the function y as equated to x cubed minus 3x squared minus 2, and we are to look for the equations of tangent and normal lines at point 1, negative 4. Note that the complementary data provided is a point, which tells us that we can look for the functions later using point-slope format. That is y minus y1 as equal to m times x minus x1. And since we already have y1 and x1, the next thing we need to look for is m. M, or slope, is determined by taking the derivative of the function. As m is just y prime, take the derivative of the whole function. Since each of the terms in the function can be separated, it would be easier if we distribute the derivative to each, thus having m as the derivative of x cubed less 3 times the derivative of x squared minus the derivative of 2. At this point, the derivative of 2 is then zeroed out. So moving on with the differentiation. M is then 3x squared with the derivative of x through chain rule. The second term has the constant negative 3 times the derivative, which is 2x, with dx upon dx, again by chain rule. Dx over dx is 1, simplifying the whole equation, making m as 3x squared less 6x. This is the equation of the slope of the function. And taking the relative slope at point 1, negative 4, m is equal to 3 times 1 squared minus 6 times 1, which gives negative 3. Now we are ready to look for the equations of tangent and normal lines. Starting with the tangent line, use the point-slope form. Y minus y1 is equal to the slope times x minus x1. Plug in available data such as y1 of negative 4, x1 of 1, and tangent slope of negative 3 to come up with y plus 4 as equated to negative 3x plus 3. Arrange the terms to have 3x plus y as equal to negative 1. This is the standard form of the tangent line. Next is to look for the equation of the normal line, still using point-slope form, but this time, the slope should be the normal slope. Then since what we have is the tangent slope, we use the relationship that the tangent slope is the negative reciprocal of the normal slope. Place this into the point slope format and plug in the given parameters, making y minus negative 4 as equal to the negative of 1 over negative 3 multiplied by x minus 1. The negatives of the slope cancel out, and by cross multiplication, the function becomes 3 times the binomial y plus 4, and this is equal to x minus 1. Distribute the constant and have 3y plus 12 as equal to x minus 1. Arrange the terms to have x minus 3y as equal to 13. This is the equation of the normal line.